The easiest way to solve this function and find all the complex roots is by first factoring it as a difference of cubes. So I'm going to write the formula for that up at the top. And then over here in the top left, I'm going to identify my a and b values, which I find by taking the cube root of each of my terms. The cube root of x cubed is x, and the cube root of 27 is 3. Now I'm going to take my a and b. Everywhere I see an a in my formula, I'm going to replace it with an x. Everywhere I see a b in the formula, I will replace it with a 3. So this is going to turn into x minus 3, x squared plus 3x, and then 3 squared is 9. So now I have my polynomial broken up into two factors. I can take the first factor and set it equal to 0, and I can solve it pretty easily. I just add 3 to both sides, and I get that x equals 3. So I have one of my 3 total solutions. And I know that I should get 3 solutions because the highest exponent of my original polynomial was a 3. To find the other 2 solutions, we're going to have to solve this quadratic function. And in my opinion, the easiest way, or the most consistently easy way to do this, is to use the quadratic formula. So let's identify a, b, and c. A would be 1, b is 3, and c is 9. And then I'm also going to write the quadratic formula up at the top here, just as a reference. It's really important that you're using the correct formula, because even if you do everything else right, if you have your formula wrong, you're guaranteed to get a wrong answer. All right, so let's plug everything in. B is 3, so negative b would be negative 3. And then I would have 3 squared minus 4 times 1 times 9. And then 2 times a is 1. The next thing you want to do is figure out what is the number that really goes underneath the radical. So I would take all these numbers and put them in your calculator without the square root. And when you do that, you're going to get negative 27. So I'm going to rewrite this. Oops, I meant to use red. We're going to rewrite this so that you can see the simplified version of it. And now all we have left to do is worry about how to simplify that radical. So we've used the quadratic formula, now it's just simplifying. So I'm going to take 27 and I'm going to do a factor tree. When I think of 27, I think of 3 times 9. 3 is prime, I can't simplify that anymore, so I'll circle it. And then 9, the only option is 3 times 3. So I have 3 3's, which when you think about it kind of makes sense because at the beginning we took the cube root of 27 and got 3. But now that I'm looking at this as simplifying a square root, what I'm actually looking for are pairs. So I have a pair of 3's here. Whenever you have a pair, you can take that one of those to the outside, and then the other stuff that didn't have a pair stays underneath the radical. So here's what we have. Negative 3 plus or minus. I can take out one of the 3's, so that goes on the outside. I can also take out an I. And the reason is because I have this negative in front of the 27. I hadn't mentioned that yet. So there's 2 things we're simplifying. We're simplifying the 27 with a factor tree, and then we're also taking out the I that comes from that negative. And then left over under the radical, we have this 3 right here, the one that didn't have a pair, that stays underneath as well. And then everything is over 2. Now the last thing we need to check is all of our outside numbers, all 3 of them. So I'm talking about this negative 3, this 3, and this 2. Is there anything that we could do to reduce all 3 of those numbers? And the answer is no, there is not. So that means this is my final answer. There's nothing else I can do to simplify.